Okay, so today we're going to be talking about Advanced General Laboratory Challenge number 3, using Boolean logic gates to design and implement a 2-bit binary multiplier circuit. And so first, before we can go any further into the design and implementation of this binary multiplier circuit, we're going to have to introduce the components. And so in order to do that, we have to talk about Boolean logic gates. So Boolean logic gates are given by these sorts of symbols. Shown here are 7 of the most basic Boolean logic gates. There is this one, which is known as the AND gate. We have the OR gate, the NOT gate, the NAND gate, the NOR gate, an XOR gate, and an XNOR gate. Now these 7 gates are, amongst, like I said, the most commonly used ones, but fortunately for the purposes of this challenge lab, we're only going to be focusing on these 3 gates right here. The circuit that we've designed only requires AND, or NOT gates. So, we don't need to pay attention to these ones at all. So let's go into AND, or, and NOT gates. The first one we have is an AND gate. So what these gate circuit diagrams are, we can break them down into, well, what do these gates do? A logic gate is simply a way of taking 2 inputs, manipulating them in order to get a desired output. So in this case, the inputs here are given by these 2 wires, and the output is given by this one. A and B are both inputs, and the output for an AND gate is given by A dot B. So this right here is what symbolizes, this means AND. So this is read as A and B. And so these can get broken down into what are known as Boolean truth tables, and you should be able to also talk about these in words as well. So what does an AND gate do? An AND gate, in words, gives a high output only if all inputs are high. So what does that look like as far as this truth table goes? If we have 2 low inputs, low, low, we're going to have a low and a high, still a low and a low, and 2 high inputs are going to give a high input. So basically an AND gate, once again, will only give a high input if all of the inputs are high. The next one we're using is an OR gate. An OR gate is symbolized by this crescent-shaped moon gate, and what an OR gate does is it, in words, gives a high output if 1 or more inputs are high. So it sort of like sniffs out high inputs. So for example, 0 and 0 result in a low input. 0 and 1, there is a high input there, so it would return a high input. 1 and 0 gives a high input. 1 and 1 also, because in all 3 of these cases, there is at least one high input, so the output is also going to be high. So that's an OR gate. And the final one is the simplest of them all. It's simply a NOT gate. And what a NOT gate does is takes the input and inverts it into, whatever the other binary bit would be. So for example, in words, it just inverts the input. That's all. So for this truth table here, it's a really simple one to fill out. We have 0 be turned to a 1, and 1 would turn into a 0. That's all a NOT gate does. And they're really useful for scenarios in which, this one logic scenario isn't quite working out right. You can negate it with a NOT gate, and sometimes that'll help clear up a lot of things. So now that we've seen our 3 basic logic gates, AND, OR, and NOT, let's talk about combining them. So for example, combining logic gates. Shown here is a very basic schematic of taking 4 inputs, A, B, C, and D, and then combining them to get one output. So what is this mystery output going to be? Well, the first thing we see here is an AND gate. So A and B. So this output would be A and B. Here we have C and D. So this is C and D. So for this last AND gate, we have A and D and C and D. So this output here equals A and B and C and D. And what this will do, since we're multiplying all of these bits together, it'll give a high input, or high output, only if all inputs are high from A, B, C, or D. Because If any one of these are 0 at this point, these AND gates will read 0, and then you'll feed a 0 into one of these, and then you'll get a 0 out here if any of A, B, C, or D are 0. And so this seems pretty straightforward for how this works. Let's try another one. So we've modified this one just a little bitty bit. If you look at the past logic gate we had two AND gates feeding into an AND gate. In this scenario, we now have two AND gates feeding into an OR gate. So an AND and an AND, oops, let's put C and D here. A and B is what this output would be, A and B. This output, C and D input, will give us C and D. However, now we're feeding both of these into an OR gate. So this output for here will be A and B or C and D. So what this will do is, if any of these are zeros, so for example, 0, 1, 0, 1, this will give us a 0 output because this AND sees a 0 output because this AND sees a 0, and then both of these zeros will give a 0 for the out. But if any one of these two, if either one of these inputs has two 1s in it, so for example 1, 1, 0, 1, this will give a 1, this will give a 0, but a 1 and a 0 for an OR gate gives us a 1. So in words, this OR gate basically finds if there are any pairs of 1s for these A, B, C, and D. Okay, so now that we did that, we need to go to the problem at hand. We're dealing with a binary multiplier. And like I said earlier, we're dealing with multiplying any two numbers between 0 and 3 expressed in binary. Now, we're already familiar with multiplication. You're used to, if someone says 3 times 3, oh, that's equal to 9, right? Well, in order to do the multiplication you want to do here, we first have to convert this into binary. So, for example, the numbers 0, 1, 2, and 3 in binary are equal to 0, 0, 0, 1, 1, 0, 1, and 1. So if we wanted to take an expression such as this and convert it into binary, we're going to wind up with what looks like 1, 1 times 1, 1 equals 1, 0, 0, 1, because this is binary for 3 times 3 equals 9. And as you can see here, we have 1, 2, 3, 4 bits. Each integer in a binary one is a bit. So two sets of 2-bit inputs equals one 4-bit output. And that's the reason why we're only multiplying between 0 and 3, is because after 3, binary numbers start getting expressed in 3 or more bits, so we have to stop at 3. So, how do we take this problem of binary multiplier and put it into what we've seen with logic gates and truth tables? Well, as it turns out, you can take this problem of binary multiplication and make one massive nasty truth table, and that's what this looks like. This right here shows all the possible combinations of the integers 1 and 2 multiplied together, giving the product output. So here you can see that integer 1 is made up of 2 bits, A and B. Integer 2 is made up of 2 bits, C and D. So any of these multiplied together should give you, so for example, 0, 0, 1, 0. That's 0 times 2. Well, that should give us 0, which in binary is denoted as 0, 0, 0, 0. So that is still 0. 1 times 1, which was the one we saw earlier, this is 3 times 3 gives us 1, 0, 0, 1, which is 9 in binary. But now that we've got this massive nasty table, we have to break it down into something simpler. So it turns out you can take each one of these outputs and do them one at a time. So for example, we're going to do P1. So P1, given the truth table that we just saw, knowing all of the possible inputs for sorry about that, got walked in on. So anyways, I just went ahead and filled out the rest of this table. And so what we know for the first input from our gigantic, massive, ugly truth table is that, as we can see here, for P1, all of the values are 0 except when all inputs are 1. So we have a 1 here, but these are all going to be zeros. So now how do we take a truth table such as this ABCD, and make it into a logic gate system? So we have 4 inputs and 1 output, and we can see that it's going to be 0 all the time unless all 4 are high. So we know that we're going to have to be able to filter these somehow. So given A and B and C and D, the logical thing to do, no pun intended, is to have two AND gates to filter out this, and then have both of these AND gates filter into another AND gate, thus giving us A dot B dot C dot D. AND gates do multiplication, so if you see all of these multiplied together, you're only going to have a high input 1 if all 4 are 1. So if any of these inputs are 0, nada, this will be 0. Which is, when you see, if any of them are 0 here, any of them, which are the first 15 entries in this truth table, we're going to have 0. So, we already saw that one earlier. That was the one we did a couple of pages back. And so now, how do we go from the circuit diagram that we've created and actually make it into a circuit? Well, that we are going to do with the help of these things called logic gates. This is what an actual logic gate is. This actually in particular is a 7408 logic gate. It's a quad input AND gate. So we're really using a lot of these. So you can see here, for these pins, we're going to have the input like A will go into 1, B will go into 2, and then go through this logic gate, and 3 is going to give A dot B. This whole thing, you know, that's just a schematic. What do these actually look like? Tiny thing right there. So now, suddenly, our problem is starting to turn three-dimensional. What we're going to do now is go figure out how to implement this into a circuit board. Okay, so now we're going to actually make the circuit. And so the one that we're going to build is the one for the first output, P1, which is simply A and B going into an AND gate, C and D in an AND gate, and the outputs of both of those being fed into a third AND gate. So what I have here is this IC circuit that I told you about earlier. I've already put power across it. That's what these orange cables are. And then so simply, you would just start putting things in the pins. So for example, this will feed from A, which we've electrified as this strip here. So A will go into one, and B will go into the other. So this goes into the second one, and we have B. And then the output of these two, which will come out of this pin right here, is A and B. And the next one we want is C, and this one, feeding into another AND gate, and D, feeding into another AND gate, D. And then both of these, the output of this, which is this black wire, representing C and D. So here's the output for A and B, here's the output for C and D, and then what we're going to do is combine these both into one more logic gate, one more AND gate. So we're going to have A and B and C and D. And then so this one right here is going to be our output, this one right here. So as you can see over here, on this side, we have an output signal. And depending on how you flip your switches and so forth is how you're going to get different signals and so forth. So this is how you build one of the single circuits. Now, we've already built one of the AND gate circuits, and that, all four of them put together, is this board right here. What this actually represents is, this is the binary multiplier. This right here is actually P1, this circuit. This is P2, this is P3, through here, and these two down here are P4. So what this will do is, given any two inputs, it will give them as outputs here. So if we power this board, for example, right now, all of these are 0, and so our output, which are these lows, are 0. So for example, if we were to multiply, let's say, 3 and 3, like we showed earlier, so that would be 1, 1, 1, 1. Notice that our output now is 1, 0, 0, 1, which is 9 in binary. So 3 times 3 is equal to 9. And say we do 2 times, say we do, let's see, that's 1 times 2. That's equal to 0, 0, 1, 0 in binary, which is 0. So overall, this is the final product. This is a binary multiplier as done by logic gates. So we got to see how to go from the logic gates onto the board, and then from the entire board, the entire circuit. So all of these four parts, P1, P2, P3, and P4, were done the same style as the other ones. They took more complicated logic gates, but the details of that you can see in the lab notebook. But this is a binary logic multiplier circuit, and this is an awkward ending. So I'm done now.